For most of my career, one question has consumed my thinking above all others. Is the universe our eyes can see and our instruments can measure truly everything that exists? Or are we perched on a thin three-dimensional layer, suspended inside a far vaster multi-dimensional cosmos, hidden beneath the quiet countryside straddling France and Switzerland? Buried under that landscape sits a 17-mile ring of superconducting magnets, the Large Hadron Collider, where subatomic particles are hurled into one another at speeds so close to light itself that the difference becomes almost meaningless. Its original purpose was always to recreate the searing conditions of the universe's infancy and expose the raw ingredients from which matter is built. But lately, strange irregularities buried in the data from these violent collisions seem to be pointing towards something even more staggering than a newly discovered particle. In the aftermath of these subatomic impacts, measurable quantities of energy appear to simply disappear. And yet one of the deepest laws of physics insists that energy cannot be destroyed. It has to go somewhere. The numbers hint at something extraordinary. That this energy may be slipping out of our three familiar dimensions entirely, escaping into hidden, microscopic extra dimensions coiled up just beneath the surface of everything we know. If these vanishing energy signals are what many of us now suspect, then CERN may have unknowingly stumbled across one of the most consequential frontiers in the history of science. This would not simply be the discovery of a new particle. It could be our very first evidence of an unseen realm. Proof that the universe is larger, stranger, and infinitely more layered than we ever dared imagine. To understand the true weight of what this data might be telling us, we need to step back and look honestly at the reality we move through every day. Consider everything you've ever touched, every place you've ever stood, every star you've ever gazed up at. All of it exists inside a framework that feels utterly fixed to human perception. Three spatial dimensions define our world: side to side, forward and back, up and down. These three directions have formed the stage on which the entire story of human civilization and seemingly the universe itself has unfolded. For thousands of years, we assumed that was the complete picture. Our brains evolved to hunt, to gather, to build shelter on the surface of a three-dimensional rock. We never needed to sense the universe at the quantum scale or across cosmic distances, so our instincts remain crude tools for grasping either extreme. Modern physics has taught a humbling lesson again and again. Human intuition is a poor guide to the actual architecture of reality. To grasp how an entire dimension could hide in plain sight, picture a long, heavy power line stretched across an empty highway beneath a fading sunset. Standing a mile away, that cable looks like a perfectly one-dimensional thread. It has length, nothing more. You can point left along it or right along it, and that's the whole story from that distance. Now imagine walking toward it, closing the gap until you're standing directly underneath. Imagine further that you could shrink down to the size of an ant crawling along its surface. That ant experiences something entirely different from what you saw a mile away. It can move forward and backward along the wire's length, yes, but it can also circle clockwise and counterclockwise around the cable's curved girth. What looked like a flat line from a distance actually conceals a second curled-up dimension, one that only reveals itself once you get close enough to notice. That simple shift in vantage point is the seed of one of the most powerful ideas in theoretical physics. Back in the 1920s, pioneering thinkers Theodore Kaluza and Oscar Klein realized that this same principle might apply to the very fabric of space. We perceive only three dimensions around us, but what if additional dimensions exist, curled so impossibly tight and so microscopically small that human senses could never register them? This isn't a suggestion of parallel timelines or alternate realities in the science fiction sense. It is a claim about literal physical directions in space, directions you could point toward if only your finger were small enough to trace them. Picture, at every point in the space surrounding you right now, tiny extra dimensions folded into intricate microscopic shapes. Dimensions a billionth of a billionth the size of a single atom. You cannot sense them. You cannot travel through them, not with a car or a rocket or a planet's orbit. Those objects only ever move through the three large extended dimensions we know. But to something as small as an electron or a photon, these hidden folds are entirely real. They form the concealed terrain of the quantum world. This is precisely where the Large Hadron Collider becomes central to the story. No microscope, however advanced, can peer into dimensions that small. The only method available for probing space at that unimaginable scale is to collide particles together with staggering, violent energy. We use energy itself as our lens, and what we search for is a crack in the structure of reality, a signature revealing that some particle has slipped, however briefly, into one of those hidden folds. So how exactly do scientists use the collider to hunt for something that can't be seen directly? When protons are accelerated to 9,999% of the speed of light and smash head-on into one another, the result is a miniature, concentrated fireball of pure energy. From that burst, new subatomic particles are born in an instant. Detectors the size of cathedrals, essentially colossal digital cameras, track the trajectory, velocity, and mass of every fragment that flies outward from the wreckage. According to one of physics' most unbending laws, the total energy and mass entering a collision must exactly equal what emerges afterward. The books must balance perfectly. There are no exceptions, except, it seems, when there are. What happens when the ledger doesn't balance? When supercomputers crunch the numbers and a slice of the total energy has simply vanished? Picture two billiard balls colliding at 10 miles an hour and drifting apart afterward at only 1 mile an hour, with no explanation for where the missing momentum went. Within our familiar three-dimensional world, a disappearance like that would be a flagrant violation of physical law. This missing energy isn't evidence of a broken machine. It's the signature of something moving unseen, the trace of a ghost. This brings us to one of the most curious open puzzles in modern physics. Think about gravity. It feels powerful enough when you struggle to leap off the ground or haul heavy boxes up a staircase. But in truth, gravity is astonishingly feeble. Consider a small refrigerator magnet. The entire planet Earth, a colossal sphere of rock and iron weighing something on the order of 6 trillion kilograms, is exerting its full gravitational strength to hold a tiny metal paperclip against the floor. Yet a cheap magnet no bigger than a coin can reach down and yank that paperclip straight up into the air, defeating the pull of an entire world without effort. Electromagnetism outmuscles gravity by a factor in the neighborhood of 1 billion. For decades, theorists have wrestled with why gravity is so wildly diluted compared to the other fundamental forces. String theory, the framework at the center of this entire investigation, offers an elegant answer. It suggests gravity isn't actually weak at all. Instead, gravity may be the only force not confined to our three dimensions. Light, magnetism, and the nuclear forces remain permanently bound to our three-dimensional layer of reality, while gravity alone is free to leak outward into the extra dimensions. Imagine standing in an open field talking to a friend. If every sound wave you produced were funneled through a narrow, solid tube directly into your friend's ear, your voice would arrive loud and unmistakable. But remove the tube and the sound disperses in every direction through open air. By the time it reaches your friend, it sounds thin and faint. Gravity, in this picture, is spreading outward into those tightly curled microscopic dimensions we described earlier. What we experience is only a faint remnant of its true strength, because the overwhelming majority of it has spilled into a hidden geometry we cannot perceive. This is exactly what researchers are hunting for within the collision data at CERN. During those ferocious subatomic impacts, scientists are searching for a heavy, elusive, force-carrying particle associated with gravity, the graviton. The working theory holds that for the briefest fraction of a second, a collision might produce a graviton, and that graviton then escapes immediately, vanishing into an extra dimension and carrying a small portion of energy along with it. When detectors register that missing energy, they aren't merely flagging a mathematical discrepancy. They may be witnessing a particle step through a doorway into another realm entirely. Sit with that for a moment. The reality you inhabit every single day may be concealing something both unsettling and extraordinary. We've established that energy appears to be disappearing inside CERN's accelerators, and that it may be escaping into microscopic extra dimensions. But the instant you accept that possibility, you run headlong into a profound and disorienting paradox, one that upends our most basic assumptions about distance, separation, and the structure of the cosmos itself. To understand this paradox, start with a fact we all take for granted: the reality of distance. To get from your home to the grocery store, you must physically cross a fixed span of space. Throw a baseball across a wide field, and that ball has to travel through every inch of the air separating you and your friend. We treat space as a rigid, empty container, one that guarantees a fixed separation between objects, keeping our world orderly and predictable, ensuring that distant things cannot suddenly reach us without first crossing the intervening void. But if the fabric of reality contains hidden, folded dimensions through which particles of gravity can travel, then that rigid container may be nothing more than an illusion. The separation between objects may not be what it appears to be at all. Picture an old paper road map, the kind once spread across a car's dashboard during a long cross-country drive. Trace a route on that flat sheet from New York to Los Angeles, and the distance looks immense. An ant crawling across that paper would have to march tirelessly across every inch to complete the journey. That ant represents us bound entirely to a three-dimensional way of seeing the world. Now imagine folding that map neatly in half. Suddenly the dot marking New York and the dot marking Los Angeles are pressed back to back. With a needle, you could pierce straight through both cities in a single motion. If the ant witnessed this, it would be utterly bewildered. From its flattened point of view, you had just crossed an immense distance in an instant. But you never moved faster than anything. You simply stepped into a higher dimension, passing through the space above the paper and bypassing the ordinary notion of distance altogether. At the quantum level, the extra dimensions proposed by string theory may behave exactly like the folds in that map. Space, in this view, isn't flat and rigid. It's complex, folded, and woven together in ways the human mind struggles to picture. When a graviton is born in a violent collision at CERN and then disappears, it hasn't ceased to exist. It has simply stepped off the flat page of our reality and slipped into the folds, taking a shortcut through the hidden geometry. And here's where the paradox truly bites. In physics, every doorway swings in both directions. If a particle of gravity can leak out of our three-dimensional space into a higher dimension, the strict logic of quantum mechanics demands reciprocity. Energy from that hidden, higher dimensional realm should, in principle, be capable of leaking back into our world as well. For the whole of human history, we've believed our universe to be a closed, secure, self-contained system, that the walls of our reality were impenetrable. But the missing energy at CERN hints that our universe may in fact be porous, like a sponge. If a microscopic particle can slip through those cracks, it implies our universe is in constant, quiet contact with a realm we cannot see, cannot feel, and can barely describe mathematically. If gravity is leaking out, we are forced to ask an unsettling question in return: what exactly might be leaking in? Are there forces or even entire structures tucked inside those microscopic folds, subtly shaping our universe without our knowledge? The closer physicists look at the smallest constituents of matter, the more it seems possible that our vast, sprawling universe might actually be a thin, porous membrane adrift in a far grander ocean. Set aside everything you assumed you understood about the structure of reality. We've discussed energy slipping out of particle accelerators and gravity spilling into hidden, microscopic folds within the fabric of space. Now we push that idea to its most extreme, most awe-inspiring logical conclusion, the point where human intuition simply gives out. In the advanced mathematics of string theory, there's a concept known as a membrane, or more simply, a brane. A brane is essentially a slice of space. A two-dimensional brane would resemble a flat sheet of paper, but the universe we inhabit, the one filled with everything we've ever experienced, appears to be a three-dimensional brane, an entire reality unfolding across a three-dimensional surface that floats within a much larger, higher-dimensional expanse physicists call the bulk. Picture a long loaf of sliced bread. Each individual slice represents a complete three-dimensional universe, complete with its own stars, planets, and galaxies. Our universe is just one slice within that immense cosmic loaf, and like any slice of bread, it has neighbors. Recall the earlier point about the fundamental forces. Electromagnetism, including all visible light, remains permanently fixed to our particular slice. Switch on a flashlight, and that light can never leave our universe. It's trapped on our surface. This is why, gazing up at the night sky, you only ever see stars belonging to our own slice. You're blind to everything beyond it. Gravity, though, behaves completely differently. It isn't glued down. Gravity alone is capable of rippling through the higher dimensions, moving freely across the gap, separating one slice of the loaf from another. This single mathematical distinction offers a breathtaking possible answer to one of astronomy's greatest unsolved mysteries. For nearly 100 years, astronomers have puzzled over what we call dark matter. When we measure how fast entire galaxies rotate, classical physics predicts they should simply fly apart, torn loose from their own centers. There isn't nearly enough visible matter, not enough stars, not enough planets, to hold them together gravitationally. In fact, roughly 85% of the mass in the universe appears to be entirely invisible. It emits no light and reflects none, yet exerts an enormous gravitational pull that keeps galaxies from tearing themselves apart. For decades, physicists have built extraordinarily sensitive detectors deep underground, hoping to catch a rare, exotic dark matter particle passing through our world. So far, they've found nothing at all. But what if we've simply been searching in the wrong place? What if the reason dark matter cannot be found within our universe is that it doesn't actually reside inside our universe at all? Imagine living in an old, densely packed apartment building. Your unit sealed behind perfectly soundproof, windowless walls. You cannot hear your neighbors and cannot see them. You're entirely isolated. Now suppose the person living directly above you drops something enormously heavy onto their floor. Even without seeing it, you would feel the vibration shake your own ceiling. If you had no idea other apartments existed above you, you'd be baffled, convinced some invisible phantom force was shaking your walls from within your own room. You might measure its strength and call it dark matter. This is the disorienting possibility hinted at by the mathematics unfolding at CERN. When telescopes detect the immense gravitational pull attributed to dark matter, they might not be observing a cloud of invisible particles drifting through our own universe at all. They might be sensing the gravitational echo of an entirely separate universe, hovering a fraction of a millimeter away from our own along a higher dimension. The dark matter binding the Milky Way together could, in this view, be the gravitational shadow cast by a massive parallel galaxy occupying the neighboring slice of bread. There could be parallel stars, parallel planets, perhaps even parallel forms of life existing in the very space you occupy right now, separated from you only by a microscopic gap along a fourth spatial direction. You cannot see them because their light remains sealed within their own universe, but you may be able to feel their tremendous mass pressing against the fabric of our own reality. What we perceive with our eyes may be only a single page torn from an unfathomably thick book. We've traveled through the mind-bending landscape of string theory, envisioning extra dimensions, microscopic folds, and parallel universes stacked like slices in a loaf. It's a stunningly elegant framework. It offers a compelling explanation for gravity's astonishing weakness. It provides a logically satisfying account of dark matter's ghostly pull, but now, as a physicist, I have to bring us back down from these mathematical heights and set our feet on the cold concrete floor of the experimental laboratory. Here is the uncomfortable truth. Mathematics, however beautiful and internally consistent, is not reality until physical evidence confirms it. For years, protons have been smashed together inside the Large Hadron Collider. Billions of collisions every single second in the ongoing search for that tiny fleeting deficit of energy, that faint whisper of a graviton escaping into the bulk. Finding that signature is like standing inside a roaring hurricane, deafened by howling wind and thunder, straining to hear the sound of a single pin dropping onto wet grass. Consider the sheer scale of the challenge. A single collision event at CERN produces a chaotic spray of hundreds of ordinary subatomic particles, quarks, gluons, muons, photons, scattering outward in every direction, a blinding burst of quantum debris. Supercomputers must sift through a relentless flood of data, painstakingly reconstructing the exact trajectory and energy of every fragment of matter just to determine whether the final accounting comes up short. Researchers are, in effect, hunting for a phantom thief hidden inside a crowd of billions. And while there have been tantalizing fluctuations, faint whispers suggesting a sliver of energy is unaccounted for, none of them have yet crossed the rigorous threshold demanded by scientific certainty. In experimental physics, a hint is never the same thing as a discovery. Until the evidence is airtight and undeniable, the escaping graviton remains for now a mathematical ghost. This absence of definitive proof forces us to reckon honestly with the limits of our current tools. What if our instruments are simply too blunt for the task at hand? The Large Hadron Collider stands as one of humanity's supreme engineering achievements, and yet, measured against the scale of the cosmos, it barely registers as a spark. If these extra dimensions are curled tighter than even our most optimistic estimates suggest, the sheer amount of energy needed to pry them open, to force a particle across that dimensional threshold, could be almost incomprehensibly vast. It would be like trying to crack a massive steel vault using nothing but a plastic spoon. Truly accessing the bulk, routinely sending particles into higher dimensions and confirming their return, might require a machine that circles the entire Earth, or one stretching the distance between the Earth and the Moon. This is the hard truth we must confront as a species. Nothing guarantees that the universe owes us an explanation conveniently sized to fit within our present technological reach. We are biological creatures, confined to a small rocky world, bound within 3 dimensions, straining to peel back the curtain on the deepest architecture of the cosmos. The mathematics insist these higher dimensions must exist. The equations demand it. But the universe may have concealed them at a scale so impossibly small, or behind an energy requirement so staggeringly large, that we may never fully cross that threshold ourselves. Does that mean the effort has failed? Does it mean the search is pointless? Absolutely not, because the act of searching has already transformed who we are as a civilization. Every time our machines are pushed to their absolute limits, we learn more about the underlying fabric of reality. We eliminate the impossible. We narrow down the hidden places where truth might be waiting. We remain, in a very real sense, imprisoned within our own 3 dimensions. But we are a species that has learned to see the bars of that cage. We know roughly where the doorway sits. What remains is discovering how to turn the handle. Now imagine the day it finally happens. Picture some ordinary morning years from now when the supercomputers at CERN finish processing the results of an unprecedented run of high-energy collisions. Physicists gather around their monitors. They check the calculations once, twice, 100 times over, and no error emerges. A massive, undeniable deficit of energy has been recorded, one that clears the gold standard of statistical certainty. On that day, humanity will have caught its first confirmed glimpse of a graviton slipping through the cracks of our reality. In that single, quiet instant, our entire understanding of existence will fracture and reassemble itself. It would rank among the greatest scientific revolutions since we first understood that the Earth circles the Sun. Because the moment we prove a particle has crossed into a higher dimension, we are compelled to accept that our whole 3-dimensional universe is merely a single membrane, floating within an almost unimaginably vast higher dimensional expanse. And that realization carries us to the true climax of string theory, to a possible answer for the very origin of everything. For decades, the standard account of our beginning has been the Big Bang, a microscopic point of infinite density that violently expanded out of nothing at all. But honestly, that explanation has never felt fully satisfying. It leaves something essential unaddressed. Where did that initial seed come from? What actually triggered the expansion in the first place? If our universe truly is a flat sheet adrift within a higher dimensional space, then it isn't alone. As we've discussed, other sheets, other brains, may be rippling and drifting through that same hidden void. Picture two enormous parallel sheets floating close together in the darkness. Over the course of billions of years, the gravitational attraction between them draws them steadily closer, accelerating, rippling, until at last they collide with tremendous force. When two vast, energetic universes slam together across a higher dimension, the resulting burst of kinetic energy is almost beyond comprehension, an instantaneous inferno of heat and radiation erupting across the entire surface of both brains. To any observer living within that membrane, that explosive flash of light and heat would look exactly like the Big Bang. The implication is profound. Our beginning may not have been a singular, unrepeatable act of creation springing from nothingness. It may simply have been the outcome of a physical collision occurring in a higher dimension. And if these brains continue drifting apart and colliding again across immense stretches of time, then the Big